human flesh and just getting hungrier. Okay. Last time, speaking of mythological things. Yeah. Last time we talked about Jahn Teller's distortion, and we were leading into what's often called the Peierls distortion for solids. We talked about cyclobutadiene having a D4H symmetry, and it will distort. And what will happen in this distortion? Actually, I should probably. Yep. And the symmetry gets reduced, right? And then we drew the MO diagrams for this thing, or at least the Huckel diagram. And then we said it will distort. And what happens to the electronic states that were degenerate? Yeah. They distort. That changes their energetics, and we arrive at a closed-shelled system. And so this happens throughout much of chemistry, one, to prevent paramagnetism, if possible. And this also happens in surfaces, and you guys have knowledge of this, or at least intuition about when this will happen. So we talked about a molecular system, and what we're going to do now is we're going to go away from a molecular system to a periodic system. We're going to check out the 1D hydrogen chain again. So in solids, we said that this is called Peierls distortion. Some people get really grumpy if you put an apostrophe here. To me, it doesn't really matter a ton, but others get mad. So we're going to consider, again, our friend, the 1DH chain, with a bit of a twist, with 2 H atoms in a unit cell. Of length 2A. Yes, you guys did do this. Band structure. Y-axis. Yep. X-axis.
0 to
pi
over 2a k vector.
Yep. What was that?
Can we not draw pi, or can we not draw 0 and then pi over 2a at k?
No, you can't do that anymore because we've increased our unit cell length. So it's gone. But is it really gone? No. Okay. What is this going to look like?
Wait, so I folded it backwards.
No, it's right to fold it backwards. Let's just draw it out here. Okay. How many orbitals in my unit cell? 2. How many bands do I need to draw? Okay. First band, what's it going to look like? Or lower energy band? Yeah, goes whoop, like that. What about the other one? Yeah, meant to be mirrored. Where's my Fermi level? Yep. Because now we have one band that's completely full, as we should, because how many electrons are in our system? 2. 2 electrons are in our system now. Okay. Now, at k is equal to pi over 2a. Oh, that was close. Let's draw out what the block functions look like. We'll mark the unit cell. Okay, if we shade these guys, remember this band was the sigma band. What was this guy up here, the blue one? Sigma star. So now we're at the zone edge. How do I have to fill this bottom one in? Yep. These two are the same. Yep. Here? Same. Now, top one was an anti-bonding one, right? Which one do you want me to shade? Second one? Oh, shame on you guys. I wanted the left one, but we'll do what you want to do. Here, how should I shade this next one?
Oh, wait, you said you want an anti-bonding.
Mm-hmm. It's right. Nope, something's wrong there. Remember, phase change between the block functions.
Oh, so no.
I was right.
What about here? Switch back, yep. Okay. Right now, is there a difference between these two?
If you're looking at a periodic system?
Yeah. Yeah, these are degenerate, hence why they meet up at the exact same point. Does that seem reasonable? Okay. So yeah, those two have the same energy in our infinitely long, evenly spaced 1D hydrogen chain at the zone edge. Is a 1DH chain favorable at room temperature and pressure? No. No. Under really high pressures, you can make it happen. Yeah.
Would that make air just solid if we had a lot of issue?
I mean, we don't really know, but we can look at Jupiter and some of the things that come off of there. And there's still gaseous is technically, for what we know, is still a gaseous giant. But there's diamond on Jupiter. There's superconducting hydrogen on Jupiter. Like there's a bunch of other stuff. So the answer to that riddle is probably it is solid as you go down, or at least really, really dense. And then as we go up through the atmosphere, it becomes gaseous. However, do we really know that?
We should just send someone to
It'll be fine.
Yeah, they maybe make it. Better than, what is it, Venus, where it rains acid rain on you. So. Sulfuric acid. And it's also incredibly hot there. So the H chain, it's going to distort. What's it going to distort into? So if you had a bunch of hydrogen spaced out like this, you somehow stabilized it at a crazy pressure, you relieve that pressure, what's going to happen to it? Yeah, it's going to break apart into H2. Distort into H2. H2 units, we'll say. So if we draw our unit cell, we could pick any one of these systems to look at. How do you want these things to distort? I don't want it to migrate across the boundary. I want these two to squeeze in.
And the middle ones to be
To go in like that. So let's call this bond length alpha and this one beta, which one's going to be bigger?
Assume beta.
Yep, beta will be bigger than alpha. Okay, what consequence will that have for this band structure? Thinking of these block functions now. So they're degenerate at the zone edge when they're evenly spaced. Will these two be degenerate when you start squeezing the unit, the bond in between the unit cell? What's going to happen to these?
The ones who are the same,
Mhm.
shape, they're probably gonna end up.
Yep. These ones will get lower in energy because we're making that bond stronger. There's still anti-bonding between each of the unit cells, right? But there's still bonding within. What about these guys as we shrink them apart? Yeah, they're going to get higher in energy. So this breaks the degeneracy of the bands at K is equal to pi over 2a. So I'm going to erase this, but we'll draw it again. Ah, fine, you all go away. K, 0, pi over 2a, energy. Okay, let's plot this out again. I can't remember which color I had which. I think orange. Okay, so it's going to do this, and then it's going to level out way more. What about the top band? Start curvy and go like that. And now what have we introduced? Yep, we've introduced a band gap. Where's my Fermi energy? Yep, that's where I would define it. Okay. No, they should be about the same size. Now, let's say I wanted to wanted to plot the DOS. What's that going to look like? Yep, 2 sets of demon horns. Whoop. Are they Van Hove factors? It should be equally spaced. I'd also need to indicate my Fermi level. Oops. There's my EF, and then if I'm going to draw this thing populated, I'd shade it. Some people don't shade it, though. Okay, so what's happened to the metallic character of our system? Yep. Yep. Might be a semiconductor now, depending on how far apart they are, if we can make it happen. But a band appears, a band gap appears. Our H2 chain, I'm going to put it in quotes because really it's just a set of molecules near one another, is no longer conductive. And I think it was Neil Ashcroft who did calculations to show under pressure, at huge amounts of pressure, like terapascals, I don't know what the current number is, but hydrogen, if you could constrain it to be a one-dimensional chain, it would be superconducting. So there are people who are out there searching for this. There's actually a lot of taxpayer dollars went into a facility up at in Rochester associated with this for high pressure, and they're looking for these systems. The what was that? There is probably superconducting hydrogen on Jupiter. It also rains diamonds, which is weird. I have no idea. I would not want to get hit with that, though. The other crazy aspect of this is people are searching ways to dope or stabilize these H chains if possible, because they know that will work. The attempts so far have not been successful.
Yeah, but also don't you inherently
Mhm.
stability is not a huge part of that, just
Mhm.
inherently that it is.
Well, if you have a continuous band structure that would look like that,
Yeah.
who cares? Like if the Fermi level is normally here, who cares if you dope up here a little bit more? It still should work. They have found through shockwave experiments, so where they can pressurize a system, it is a superconductor, and it can persist for a little bit. The problem is when you do shockwave experiments, it's not static pressure, so you really can't control the system a ton. Do you guys remember how they get static pressure, or how I talked about it in the past? Yeah, the diamond anvil cells. That's how they maintain static pressure. They literally put in some stuff in the center, squish it. They look for a transition in the conductance and resistance, and also color changes through IR, because the system is fine. It's transparent through IR in certain regions, and they can suggest that superconductivity has happened. Okay. General rule, though. Which I know I've said a handful of times. Just systems want to be metals. No. They only are metals because there's no better alternative. So generally, systems do not want to be metals. They do not want to be magnets if they can help it. If let's say you had a metallic system, you calculated it out, you draw the band structure, what should you always be considering after you've drawn this band structure? So like our 1D hydrogen chain, you guys all knew that was fictitious, right? What are some key indicators to tell you that's not going to hang around very long? So, band structure, what would that tell you? Or how could you use that to say, yeah, this probably will or won't distort? Yeah, if they touch, chances are they're going to want to do some sort of distortion if possible. Densities of states. How could you, if I gave you a picture of that, how would you be able to tell, the system, yeah, they want to introduce a band gap. Of course, are there systems that will not have a band gap? Yeah, there are. There's lots of them. But if possible, the system's going to want to distort to prevent that from happening. An example, I gave you back that daily problem with cubic and alpha telluride, and you could see in there, look back, do you guys still have it? Look, pull that back out and look at the DOS. I think I just handed it back to a couple of you. Yeah, so look at that DOS. What do you notice between the two? Band gap, no band gap. Okay, if a system can, it will try to introduce a band gap.
So if there is a band gap, and it's more likely to persist.
I'm sorry, in generally, yes, if there is a band gap, it's more likely to persist. However, there are situations where, like, you can pull up any of these metals by themselves, especially some of the transition metals, and they're going to be conductive. They just have to be because they don't have enough electrons, basically, and it's going to work out to be that way. Yep, copper, silver, gold, all conductive. They're weird. It's probably better to look more in the mid-range. Consider those. Nope. These guys, I like these guys. The mid-range transition metals and higher up on the scale. Here, you get weird relativistic effects that happen. Nothing.
Isn't titanium like not highlighted?
Oh, so magnetism is something different. Yep. We're not going to have enough time to talk about magnetism, but there's mechanisms where if you understand the band structure, you can learn about magnetism pretty easily. Maybe when we're doing some calculations on Friday, maybe tomorrow, or maybe Wednesday, sorry, we'll be able to look at alpha and beta spins. So up spins, down spins, that's where magnetism sort of gets introduced. Okay?
Is molecular